Good evening from the woods of Maine. Per last lecture, I believe that we pretty much covered um most of the later Phanerozoic up to the Permian period. Um, and basically that brought together the supercontinents to make Pangaea. And Pangaea has now come together, and Pangaea is very likely the largest assemblage of continents that the planet has seen thus far. The only other contender would be Rodinia, um, but we think Pangaea was probably the biggest one. In any case, Pangaea, when it comes together, produces colossal mountain ranges. Changes the ocean's currents. It does all sorts of crazy things. Um, and what, unfortunately, it really does is it ends the Permian period with the world's largest mass extinction. And you know, for years, scientists have been trying to figure this out: why 95% of all life on the planet decided to cash out. And the problem is that we associate mass extinctions, pretty much just by media, as a large, asteroid or comet or whatever slamming into the planet. And of course, we know the dinosaurs fell victim to that. Um, but they can never find one that was around 250 million years ago, at the close of the Permian. So, there was no smoking gun for this one. However, over time, we've come to the conclusion that maybe it wasn't just the asteroids that wiped out the dinosaurs. Maybe it was more than just an impact event. Maybe the impact event was the icing on the cake, and more evidence seems to come in that that is the case. Earth was already in turmoil by the end of the Cretaceous, and the last thing it needed was a 6 mile wide hunk of iron slamming into the planet. So, anyways, that's another story. Back to our Permian extinction. This likely, as it turns out, we believe it was caused by volcanic activity resulting from the Siberian traps. Well, again, that might have just been the icing on the cake, because like the Cretaceous Tertiary extinction, the Earth already seemed to be going into mayhem tens of million years before this. And then, like a huge asteroid whacking the surface of the planet, you really don't need the largest volcanic event in the planet's history to occur while you're already having a stressed environment. So that really does seem to be the case. So mass extinctions in Earth's history, to us geologists, we kind of we call them the Big Five. There are lots of others. Some of them are big, but the Big Five are just considered the the usual, the classic list, the OG, whatever you want to call it. And the reason why we don't go further back, because there actually were bigger ones, but they were recorded, or not recorded rather, because the animals at the time were soft-bodied, and we didn't really have much to make an impression or a fossil. And they were small, and prior to the Cambrian, most things were microscopic, with the exception of some Ediacaran biota and some very late Proterozoic life forms. We do find some casts of them, as well as the stromatolites, but those we don't really put those into the mass extinctions, because there just isn't the. It's based on theoretical, and we just don't have the real evidence like we do for these. So, in any case, the Ordovician, probably the first one. These all often have some very common themes in them. 85% of species, about 445 million years ago. Primary issues might have been rapid cooling, which induces falling sea levels. When you have sea levels, whenever sea levels drop, that always seems to come with a problem, because anything that lived in those areas is obviously going to have to adapt and move or fail. And when you have high sea levels, you have a lot of continental flooding in empiric seas where tons of life is. And when you drain those, it causes a huge disruption in the life cycle, in the food chains, most importantly. So Devonian, this one, about 70%. There is some impact evidence there. Again, a rapid cooling, maybe because of the impact. And again, same thing, rapid cooling extinction event. Permian, this one's a little bit more juicy. We have massive volcanic eruption inducing huge releases of methane and CO2, rapid global warming because of that, but also rapid cooling prior to that. Whenever these erupted, you're putting in a ton of sulfur dioxide into the air, and these have a tendency to reflect sun. So when you immediately get an eruption, you have a tendency to cloud the air, and you have reflectant properties or materials in the air, and you end up actually cooling the climate. You cool the climate temporarily, and then it goes into the heating phase. And this went on up and down, up and down, up and down towards the end of the Permian. And so over time, this alone caused massive problems with the atmosphere, thus the life forms. But prior to that, and prior to this extinction event, we were noticing that the oceans were losing oxygen. They were also becoming very acidic, and then there was desertification of the land. And this is important because these things are all causing the oceans changing is the basic fundamentals of the building blocks of the food chain. If they get screwed up, well, it's like a domino effect. And then the rise of the huge mountains of the Appalachians caused a ton of problems for the atmosphere. By the weathering of it, dumped tons and tons of it sucked up CO2 out of the atmosphere. Again, the climate was cool for the majority of the part, and then once the mountains became somewhat leveled, and you didn't have that huge CO2 vacuum, well, CO2 started to build up pretty quickly towards the end of the Permian. And then you're starting to get warming. Glaciers are melting in Gondwana. You're getting no place to put the carbon dioxide. It's getting into the oceans. The oceans are now heating. They are becoming somewhat less oxygen. There's less oxygen in them. And all of these are going to contribute to the hugest mass extinction that we know of. In the Triassic, we have the opening of the Atlantic, likely a volcanic CO2 releasing event associated with that, and that essentially kept the opening of the Atlantic essentially kept global temperatures warm for the next literally 100 million years, because when you had all the volume of lava, magma generated to split the Atlantic Ocean, you raise the mid-ocean ridges, which in turn raises the sea level, and you have a lot of flooding in the continental interiors. And the flooding of the continental interiors helps regulate weather. Lots of water, weather gets regulated. Lots of land, temperatures fluctuate extremely in extremely wide ranges. So water is one of the few things that can really regulate your storm frequencies and your temperatures. And back here, when the mountains rose and you had deserts, all of a sudden you went from a very stable climate to a very crazy, rapidly fluctuating climate, because we didn't have the oceans in the interior of the seaways anymore, and we didn't have we have the desertification of land, and we all know that deserts can have very, very serious fluctuations in temperatures. And then, of course, the Cretaceous Tertiary. This is the dinosaur extinction. So what, 76% here, 80% here. Again, we had the same problems here. Here we had a very warm period of time until about 100 million years ago, and then the climate started going haywire because of large volcanic eruptive activity. You started to have cooling. The mid-ocean ridges began to stop flowing as heavily as they were, so they essentially regressed into the crust. So now the sea levels aren't as high; they're actually falling, and they're draining off of the continents, and that is now allowing weather to fluctuate much more radically than it was before. And so what was once a very stable, warm, so more or less tropical planet is now starting to become temperate. You're starting to get massive fluctuations in temperatures and storm activity because all the interior seaways of the continents have drained off. And that is also causing problems and stressing life. All right, so chart of the big five. You can see that first one here, second one here, Permian, just gigantic drop right here. Triassic, not too bad, and then the end Cretaceous one right here. So an argument, this is obviously the largest one right here, right at the Permian. These are life forms right here that basically these sort of peaked in the Cambrian life forms. We associate them these are, just associated that they're Cambrian life forms, and they existed up to about 100 million years. Paleozoic life forms peaked in the Paleozoic, and then they're still around today, but they're not quite as common. And then we have the modern day phylum, and if you notice, species kind of peaked out right here, and it stayed that way for 200 million years at least. And then with this radical extinction event, and you brought everything back down, well, it has since been climbing and continues to climb. So it really, we broke through at some point here the resistance of evolution right at about 445 species, marine species, and now we're up to almost like 700. So that's something, I don't know why that is, but that is evident. All right, late Permian extinction theories. What likely didn't cause it? The impact event. Possibilities, acidification of oceans, anoxia, large igneous providence, the Siberian traps, rapid climate change induced by all of the above, methane release, ozone destruction, stardust or nearby gamma ray bursts, maybe all of the above. So events leading up to the end Permian extinction. Prior to Pangaea, Earth was cold, had glaciers in the early Permian, meaning lots of oxygen, less carbon dioxide. Ocean circulation was efficient and waters maintained high levels of oxygen. Carbon dioxide was kept in check since Pangaea came together in the late Carboniferous. Large mountains locked up CO2 due to silicate weathering and kept carbonic acid out of oceans. Bang, life flourishes. And we know that because almost every species is almost at the same zenith that we see today, except they're just less evolved. A Gorgonopsid would absolutely tear apart a lion, but if you look at them, they look kind of similar. So whatever that, it's interesting that those two, that design not only worked the first time, but it was held true the second time. And I'm guessing that in the sixth extinction, it will probably hold true again. Pangaea interrupts ocean circulation, and oceans start to become anoxic, meaning there's not good circulation. And the gist of an ocean is oxygen gets pumped into the ocean up top, and then eventually denser water sinks, bringing oxygen down with it, and round we go. Well, when you start getting just warm, when the column's just warm, it doesn't start overturning, and guess what? Your bottom areas or just certain areas somewhere in the water column are going to start getting anoxic. And well, we all need oxygen to survive, so you know where that goes. By late Permian, climate started warming rapidly to the influx of CO2 attributed to the massive erosion of the Pangaean mountains, and there's no more silicate rocks to lock up the CO2. And the geographical location of the supercontinent literally means that the erosion is going to continue, and it's going to just keep pumping out. It's going to just keep running because water over the land, because the Pangaea, the chunk of the mountain range, is located right on the equator. With the Pangaean mountains eroded, carbonic acid begins to accumulate in the oceans from rivers dumping more carbonic acid into them. Again, that carbonic acid was locked up in the mountains, and now it's not. There are no mountains to do it anymore. Global temperatures begin to rise, causing more rain, accelerates the erosion. Oceans become more anoxic, and eventually become euxinic, and we know this because there's a formation, there's layers of pyrite that we see where we find marine deposits of this age. Due to the lack of circulation and the lack of mixing of deep waters. Sea levels start fluctuating rapidly and generally drop, a worldwide regression. Temperatures spike near the end of the Permian, and then life is already stressed in the 10 million years approaching the extinction event. And this is Pangaea in the late Permian. this sea is becoming now very, very warm. Anything up against this side is very, very warm. Um, and we have upwelling along the back area over here. But this is just going to start, and all this water is going to be warm. It's going to evaporate. It's going to go in here and just destroy it and erode everything in a very quick time. Um, and what we end up having is just tons and tons of erosion. The CO2 gets sucked out. Climate cools, but then once these mountains erode, the CO2 begins to get released, and then it ends up running into the rivers, and because we don't have the rocks to lock it up. And the rivers dump all that into the ocean, causing problems. This is just basically a quick, well, I mean, I can make it long, but it's pretty simple. Again, CO2 being released. CO2 weathers, CO2 gets locked up. Some CO2 goes up into the atmosphere, and it goes into the clouds, and it comes out as rain as carbonic acid. But if we take a lot of the CO2 out prior to it actually getting evaporated, then we don't have a lot of the CO2 getting dumped into the rivers, thus the oceans. So if we can lose it here, not a lot goes in here. But once this area gets flattened and all the silicate materials are no longer there, the CO2 ends up running into the ocean, and it starts becoming more acidic. And the more acidic the ocean comes, well, shells cannot form because they end up getting actually dissolved. Big problem. Paleoclimate of Pangaea. So you've got your tropics right here, always wet. This is, I would extend that down here too. I mean, I'm sure that this was much bigger. And then you have just giant deserts right here. I mean, when you have something like this, used to be all green before this came together. And now that it's dry, you are looking at very, very, very extreme weather fluctuations in temp. So in other words, it can just be beautiful and warm right in here, but I'm telling you, here, here, and here, and here, you are going to have massive temperature fluctuations, and that's going to really start to take its effects on global climate. And again, these are this is another Pangaea map right here. What I have done is I have outlined these areas where you have monsoon rains, and again, you're seeing just huge amounts of rain and erosion coming in here. You probably have some up here. This might be more seasonal, but this might be more constant. So you're just getting tons and tons of. That's why these mountains just got leveled so quickly, and then eventually no longer able to take up the CO2 in the air, and again, allowing it to get released into the oceans. So if we were going to look at, this is sort of a diagram I made, if we're going to look at sediments, basically showing us why we know that the marine sediment, that the oceans became anoxic, sort of near the Permian, close to the Permian, it's all right here. Anything in blue is basically telling you you've got oxygen. Anything in gray means it's becoming anoxic, and then everything in black is basically anoxic, completely anoxic. And then when you actually hit euxinic, that is when you get this pyrite. In other words, sulfur is just coming straight out of, and iron is just coming straight out of the water, because there's nothing, it's saturated. There's just, the water there's no oxygen for it to combine with, so the pyrite ends up precipitating. And right on the dot right here, you can see that this is the extinction event. So we went from good to bad to real bad, like the worst, and then it kind of stayed in this area for at least a couple million years after, before we start to see recovery. Black shales, dead giveaway. Basically, you're just getting there's nothing can break down because there's just no oxygen. You got evaporites, boom, totally a great indicator. You have just no oxygen in here. Pyrite, yeah, that's the pyrite thing. Molybdenum, I really don't know what it has to do, but again, these are all showing the fact that you have a giant dark line right here, and it's a very abrupt line at the extinction event. And you can see here, all of it takes at least 5 or 6 million years for this to start to recover. So anyway, So healthy calcare limestone forms. Then you get into here and we see these cherts. When you see cherts, basically made when you have silica, basically without the, cal, the carbonates, you know that you're in an anoxic environment, and so the cherts end up becoming truly anoxic, and then when we come out of it, you're still in a reduced oxygen area, and it stays that way up until about 248, and then you start to get into deserts and sandstone, and this is basically saying that this is a drop in sea level from everything that went on, especially especially in North America and many of the other cratons. You had an inland sea, it warmed, and then it began. The temperature dropped, sea levels went, and then everything just warmed up right at the end in the last like 10 million, and you have basically. This is indicated by the fact that you see the reduction in oxygen, because when you heat water up, it cannot hold a lot of oxygen. And then literally it just gets completely anoxic, and you end up precipitating pyrite, and then you stay in a very anoxic condition right here, as indicated by the black and the gray, and then we slowly start to come out of it. This is the Siberian traps. This is a gigantic area on the in Russia. I mean, roughly the size of the United States, I would say. And that's just what we see here. It's a good chance that this goes a lot bigger. But this is the largest single volcanic event known. There may have been others, but they've been since erased. But this is a very problematic situation for a climate that is already in distress, as I just described earlier. Siberian traps defined. All right, so the Siberian traps, they're a large area, region of volcanic rock known as a large igneous province, a lip, in Siberian Russia. The massive volcanic eruption event that formed the traps is one of the largest known volcanic events in the last 500 million years. That is true. The eruptions continued for roughly 2 million years and spanned the Permian-Triassic boundary, or the PT boundary, which occurs at 251.9 million years ago. The Siberian traps are believed to be the primary cause of the Permian Triassic extinction event, the most severe extinction event in the geologic record. The subsequent periods of Siberian traps activity has been linked to a number of smaller biotic crises, including the Smithsonian-Spathian, Oakleonian. I'm not going to try to pronounce these, but those are other extinction events around the same time. Large volumes of basaltic lava covered a large expanse of Siberia in a flood basalt event. Today, the area is covered by about 7 million square kilometers of basaltic rock with a volume of around 4 million cubic kilometers. This is estimated to have covered the entire U.S. in 200 meters of rock. The majority of materials erupted in less than 2 million years. So it happened very quickly. And imagine, I mean, look at what a small eruption does. You know, you get one in Iceland, and or the wildfires. The wildfires, they were even a volcanic eruption. They darkened the skies on the East Coast for like a week. I mean, it's a forest fire. Something like this, you're looking at, well, obviously, global catastrophe. Cross-section of the Siberian traps over time, and this is kind of important. So you have, we're going to start here, stage 1, you have nothing. 2, you get your initial sills and I'm sorry, sills and dikes coming in, feeders coming in and starting to erupt and push down on the crust. Over time, this shield begins to spread out. The area beneath begins to heat up. The magma begins to exploit the cracks, and the eruptions begin to spread in all directions laterally. And this just keeps going on while this dome builds. But what's also happened is underneath here, a lot of this stuff that's in here was coal. And this is coal that was built up in the Carboniferous. So this thing is erupting in materials that are already meant to burn. And so it's just like you've let's just erupt this through a barrel of gasoline. Essentially, is what happened, and that's what happened. That's another reason these things put out an incredible amount of sulfur dioxide. It was just unbelievable. Not to mention the CO2 and the carbon from all of the from all the coal that's down in here. So we have like a triple whammy here. You've got the heat, you've got the smoke, you've got the particulates, and man, even worse, it's burning in a coal field. So, I mean, there's still coal. There's still coal mines burning in West Virginia. They've been burning for over 150 years. So imagine what this thing did. All right, so the effect of the Siberian traps. This is what it did. Take into account that the Earth's climate was already stressing life forms. It released massive amounts of SO2, CO2 in a short period of time, creating a seesaw effect on global climate. It likely blocked out sunlight numerous times, slowing or halting photosynthesis worldwide. It accelerated acidification and anoxic conditions in the ocean. Massive release of toxic chemicals, especially mercury. And mercury is not good for anybody. Essentially sent global temperatures to possibly the highest they've ever seen on the planet. Worse, the Siberian traps erupted in a giant coal field that was created in the Carboniferous, making all of the above orders of magnitude larger due to forest fires. And the climate was driven to a bare, dry landscape, and the ocean barely able to host life. So close to a 95% fatality rate. And this is sort of how it went down. Everything's lovely here in the Permian. Trees, swamps, creatures, little mountain range here. And then you've got this gigantic eruption dumping all this stuff, acid rain, CO2, SO2, just everything. And it scorches the whole land because it's in a coal field. So all this lights up and boils a lake or whatever, and then basically kills everything. And then what you have left is this. And over time, life begins to make its attempt to come back. Summary. The end Permian extinction is the largest known of its kind, greater than 90%, and occurred at roughly 252 million years ago. Although the event appears almost instantaneous in the geologic record, however, it may have started up 10 million years prior. Life flourished for most of the Permian, and almost all niches were occupied as they are today. The Permian period started cool with some glaciations, but temperatures began to rise as glaciers melted. As Pangaea came together, a giant mountain range occupied a large area near the equator, i.e. the Appalachians. This kept carbon levels low and temps cool. Little typo there, sorry. As the central Pangaean mountains eroded, less carbon was locked up due to silica weathering, or lack thereof, and was now pouring into the oceans. Oceans became more acidic, and global temperatures began to rise. As global temperatures began to rise, ocean temperatures rose, causing oceans to become anoxic, and even euxinic, it's hard to pronounce that, in some places. Due to oceans becoming both acidic and anoxic, life began to struggle, and even worse, sea levels dropped worldwide, stressing life on the continental shelves. As the Pangaea supercontinent took shape, the climate went from a relatively stable and ocean-influenced to land-influenced in many places. Again, sorry, typo. The climate began to have major seasonal fluctuations, stormier weather patterns, large desert areas forming. Due to the central Pangaean mountains being located near the equator, large monsoon seasons caused massive amounts of sediment to be deposited into the tested sea, pushing oxygen levels lower. In other words, you put a bunch of stuff in the oceans, you're going to need to decay it, and in order to decay something, you need oxygen. Overall temperatures began to rise near the end of the Permian. Life is now very stressed, and then the Siberian traps erupted in the late Permian, dumping massive amounts of SO2 and CO2 to the atmosphere, causing huge fluctuations in global temperatures. The Siberian traps are the largest known volcanic eruptions to have occurred in geologic time, with an estimated amount of lava to bury the U.S. by 200 meters. They released massive amounts of toxins, most notably is mercury. They also ignited the coal fields in which they erupted in, which were of similar size. The end result was a global climate that went from a warm, wet, stable climate to a hot, dry, barren, unstable landscape in less than a few million years. with equally polluted oceans. Guess what loves hot, dry climates? Reptiles. And the reptiles are the ones that really reap the benefits of what happens. And they, of course, the reptiles evolve into, i.e., the dinosaurs. What was the likely cause of the Great Dying? Pangaea. State of the Earth from deep underground to the atmosphere from 300 million to 200 million years ago. This shows the extinction event quite clearly. All right, state of the Earth from deep underground to the atmosphere from 300 to 200 million years ago. So this is the boundary right here. For some reason I did not put a line in. I don't know why. I usually do. But anyways, this is the line. And you can see this is the biodiversity. This is the amount of, creatures, more or less. And they just, boom, drop. This is temperature, and it goes from cool to warm, then back to cool. The ocean, this is anoxia, and you can see it just crashes right around here, and it is driven basically way over into the anoxia and then back up again. Carbon, whatever you have, way this works is on this particular graph, life is doing well when it's high, and then when it goes down, it is real bad. So I think carbon circle. So basically, when you see this crash right here, this is basically saying that this is, things are not going well. Seawater coverage, so this is more or less, high sea level, low sea level, and again we get a huge crash right here. Siberian traps. Over here. So this is interesting. We have Pangaea converging, Pangaea integration, and then Pangaea rifting. And it's interesting that between the rifting and the coming together, right in the dead center is when you have this extinction event. That is a very interesting. I don't know why that is, but I've never seen. I didn't pick up on that before. But in any case, this is the extinction event right here, and it's clearly showing that something really serious has happened. And that's the point of that graph. Global temperature and CO2 levels. This right here is the average global temp. I'm sorry, CO2. And as you can see, CO2 cranked right at the end. We've had much higher CO2 in the past. Right now we are actually very low with our CO2. But these have generally coincided with warmer time periods. So there's a general trend down to the Paleozoic, and eventually it really crashes in the Devonian and stays very low through the Carboniferous into the Permian. And this is likely the cause of Gondwana glaciation right here. And then once the glaciers begin to melt, well, it releases water, and carbon dioxide gets freed up, and you start to see a rise in the CO2 right here. And then, of course, the temperature rocketed with it. So something big happened right here, and this is our extinction event. Pangaea about 251 million years ago. Traps up here, Pangaea. This is basically, I don't know why I put that there. Type sections of Permian Triassic. Oh, okay, yeah. This is one of the areas where we have a recording of the event of the Permo-Triassic boundary. There's also another one up in here. And we use those. Those are the two that the majority of work has been done to figure out what exactly happened. But this is Pangaea in its full glory. We would be right here. This is a gigantic Appalachian mountain range right there, and then the traps up here. Animal evolution. So this is so something that kind of came out of this is we have our common ancestor here, early reptiles, and then at around 300 million years we diverge. And the sauropsids, become the reptiles that we know today. And that includes our dinosaurs and birds, and then the snakes, taurs, lizards, turtles. And then we also we split, and we went. One group became the synapsids, i.e., the Dimetrodons, the therapsids, the gorgonopsids, what have you, and eventually all mammals and us. So we split. We basically are a reptile that's just slightly more evolved, and our split happens in about 300 million years. Again, this is sort of a tree of our evolution. And so we have a very common ancestor back here, way back here. And it splits into three. You got your vertebrae, your invertebrates. I think these are like sponges and what have you, jellyfish, whatever. These go to worms and fish. You get your jawless fish here. You get your cartilage fish here. Bony fish here. And this is just evolution, really. You could kind of just go down. And then, of course, the amphibians come out of that. And then out of that line, the reptiles become. The birds break off from the reptiles, and the mammals break off from the reptiles at about 300 million years. So that's just a very basic idea of evolution. Just another, this is kind of showing you what was in charge at certain periods of time. Single-cell organ, basically nothing. Stromatolites, single-cell organisms, bacteria, algae. Then you get your life's explosion. You get your sponges, your corals. You got your trilobites. You got your ammonites. You got your fish. And then you start to get your first plants right here in the Silurian. Lungfish starts to try to climb out. We get into insects, and then we evolve. The fish evolve into the amphibians. Sorry, the amphibians are here. And then once you get to here, the amphibians evolve into reptiles. The reptiles split. You get your mammal-like reptiles here, and then of course you have your reptile. Pure reptiles here, and then you evolve into the dinosaurs, and then the dinosaurs, of course, go into the birds, and then in the meantime, the mammals kind of show up here, but they don't really start coming anywhere, getting anywhere till the tertiary after the dinosaur extinction event, and of course the mammals take over. We become the dominant species. I don't know if I really believe that. I think the insects are. They seem to survive everything. And this is just time. You got your major eras right here, and then of course your big five: 1, 2, 3, 4, and 5. This is a very complex family tree, and you really can trace it if you really want to do it. It's right here. Here we are. Boom. Boom. But you can trace this, and you can see where they branch out, and it gets nuts. You can do. Oh, I didn't put that other one in, but there's a there is a family tree that can just make it is gigantic. So I'm going to end this particular lecture here because we're about ready to go into the Mesozoic period and into the Triassic period.